Hey everyone, Mr. Fritz here. We're going to talk about vectors and coordinate geometry in this video. We're going to put vectors on a grid system and we're just going to do some of the same stuff, but now with coordinates. So let's dive right into it. Before we begin, I've got an opening problem for you. I'd like you to pause the video and try these two problems on your own. Hopefully you can make some sense of them. If not, I will post an explanation video kind of in another video, but pause the video and resume when you're ready to check the answers. All right, here are my answers for these two problems. Check out my work or those videos if you need any help. Let's talk about vectors in the coordinate plane, in the xy plane. You don't need to write anything down here in your notes. I just want you to watch this. Here's vectors between 2 points or 2 coordinates. If I want to draw the same vector emanating from the specified points, so here's my vector. I want to draw the same vector emanating from this point and emanating from this point. And I'm going to show those vectors in component form. So if I'm doing that, really what I'm going to think about doing is I want to figure out how far to the right this vector goes and how far up it goes. So this is going to go over 2 and up 1, 2, 3, 4, 5. So if I'm emanating from this point, I'm going to go over 2 and up 1, 2, 3, 4, 5. That's a vector right there, and over 2 and up 1, 2, 3, 4, 5. So here are my other vectors, same vectors, they're just emanating from a different point. And hopefully you can see they have the same direction, they're all parallel, they have the same size, and really the components of all three of these things, if I were to kind of analyze this, would be, surprise, surprise, over 2 and up 5, over 2 and up 5, over 2 and up 5. So really all of these vectors have the same components at the end of the day of 2, 5. So that was pretty easy to see from this grid, right? I'm just counting my x step, I'm just counting my y step. But what if I showed you the same picture, but now with xy values, right? We're now on a coordinate plane. And do the vectors change? I mean, hopefully you can see that they don't. But let's think about if I were given these coordinates and not a grid to try and find the components. So really, if I'm still considering the x and y step, let's look at this red vector. I'm still going over 2 and up 1, 2, 3, 4, 5. And let's think about how I would show that. So let's call this vector r since it's red. And that's going to be given from my x step. And looks like my x step ends at -1 but begins at -3. So I can subtract, I can find the difference between -1 and -3. For my y values, looks like it ends at 4 but begins at -1. So I can find the difference between those two values to find my my step in my vertical direction. And if I do a little bit of arithmetic, I can find that this comes out to be 2 and 5. So surprise, surprise, it's the same vector as before. I could do this with the blue, I could do this with the green. Let's do this with the green, and then we'll stop there. If I look at my x step for vector g, I'm ending at +3 and beginning at +1. So this is going to be a difference of 3 minus 1 for my x step. And for my y step, I'm ending at +1 and beginning at -4. And if I do some arithmetic here, 3 minus 1 is 2, 1 minus -4 is 5. What do you know? These are the same thing. Hey, look at that. Big surprise. So what if we were just to take away the grid and now kind of look at coordinates? This is really all that vectors are in the coordinate plane. Same rules apply, adding to the same, subtracting the same, multiplying is all the same. We're just doing it with a grid. So let's kind of generalize this. If I'm just given some vector a, b in the coordinate plane, what kind of generalizations can we make? Well, I have two coordinates. I've got coordinate a and I've got coordinate b. And what I see here is that coordinate a is expressed for any coordinate a. This is x sub a and y sub a. And b is going to be x sub b and y sub b. And hopefully that makes sense from this diagram. If this is x sub b and this is y sub b, that's where the coordinate is. And if I want to find this actual vector going from a to b, then I need, let's see, in going from a to b, then I can think about the x step as how I get from here to here. And that's just the difference from x sub b minus x sub a. So the x step equals x sub b minus x sub a. And really that's like another way of just saying find the difference between your x values. And your y step is going to equal y sub b minus y sub a. This is a lot like slope, but it's not rise over run. We're just looking at just the distance, or how I get from one point to another. So it's not necessarily a slope, but it is kind of a similar concept that we're finding the distance between x values and the distance between y values. So we can say in general then, the vector, let's put this in red, the vector AB, in this case, or any case, is given by the components x sub b minus x sub a and y sub b minus y sub a. Now with slope, it doesn't matter. If you're calculating slope, it doesn't matter if you're picking 1 point first or 1 point second. It's still the same rise over the run. It does matter in this case. AB equals this vector right here, but I can take, let's try doing this. I could take a vector in the opposite direction, and I could say vector BA, which is going to be the negative vector of AB. That's exactly the reverse. This will be x sub A minus x sub B, and then over y sub A minus y sub B. So long story short, whatever the terminal point is of your vector is the number that you're starting with for your x and y components. So it's kind of from finding how you got from where you started. So just keep that in mind. All right, so that's the generalities. Let's talk about some examples. So I want to find, I'm going to give you a couple of points, and I want to find all kinds of stuff about the vectors between these 2 points. So let's go with plotting these points. P is at -1, 2. Here is P. And Q is at 3, 1. So 1, 2, 3, 1. And I'd like to find vector PQ in component form. So this is vector PQ right here. That's a vector. It's got a size. It's got a distance. It's got a size. It's got a magnitude, size, and a bearing. That's the word I'm looking for. And I can express that by finding the difference in the x step and the difference in the y step. So in general, I can write this as, for letter A, I want to find PQ. And that's going to equal from my the difference of my x values. So I'm going to put the Q first. So here's 3 minus -1. And then for my y, I'm going to take 1 minus 2. So vector PQ in component form is 3 minus -1, which is 4, and 1 minus 2, which is -1. And hopefully this makes sense. You can verify this by counting, right? I'm going over 1, 2, 3, 4, and I'm going down 1. So there's my component form right there. Really, either method works, right? You can use the visual, or you can do it arithmetically. Makes no difference. All right, next up we want to find the distance from P to Q. So what is the actual size or magnitude of PQ? And to do that, I'm going to use the Pythagorean theorem. So the magnitude is going to equal the square root of each of those components squared. So 4 squared plus -1 squared. And when that shakes out in my calculator, let's see what I come up with. The magnitude of PQ is the square root of 17, which is about 4.1. All right, so those are the easy ones. Now it's time for the bearing. So again, we have to kind of think about drawing a compass right where my vector is emanating. And let's see, let's put this in green here. If I want to find the bearing of this, I want to find how I get from north to this vector. And what I can do is I can think about the little tiny triangle, little tiny right triangle that I can make with my horizontal and vertical components. So remember, this has a horizontal component of 4 and a vertical component of -1. So if I want to find the little tiny angle that's inside of this triangle, we can call that theta. The tangent of that theta is going to equal the opposite over the adjacent, so that's 1 over 4, and I'm just going to use the positive values for now. And so the theta is going to equal the inverse tan, or the arctangent, of 1/4. And that theta, that little tiny angle right here in this triangle, comes out to be 14 degrees. Now if I want the bearing, the true bearing, I have to start from 0, and I have to go all the way to this resultant. So I'm going to go 90 degrees plus that 14. So at the end of the day, my bearing is 90 plus 14 degrees, so which is 104 degrees. So there you go. Took a couple of points, did a bunch of stuff with it, and we found all of these pieces of information. We can express the vector PQ in component form or in magnitude and bearing form. Here's a you try. I'd like you to do the same thing that we just did with these two new points, A and B, and find the same information. Give this problem a shot and resume the video when you're ready to check the answers. All right, so here are my answers for this example, and hopefully you had some luck with it, and check it over if you have any doubts. I think we're going to take a pause here, and in the next example we're going to add a little bit more points, just make it a little more complex. Nothing really all that crazy, but just turn it up a little bit with this coordinate plane vector stuff.